So I'd like to go through how to calculate concentrations and work out rates from from a loss of mass. And you would get a loss of mass where we have our reactant that's in a conical flask and we're letting a gas escape, and we're actually tracking it by the mass that it's losing. So in this particular exercise, we've got a student that's got 5.2 grams of zinc, so let's say that's the 5.2 grams of zinc in a conical flask, and it contains 225 centimetre cubed of 1 mole per decimetre cubed, so 1 molar hydrochloric acid. So the initial mass of the vessel is worked out. Its contents were 389, so when everything's in that flask and that flask is put on the balance, the whole of it weighs 389. So that's the hydrochloric acid, the zinc and the flask itself. So the student monitors the loss of mass over time, and we can see he's took results, or took measurements every 10 seconds, and we've got the mass there every 10 seconds. So he's monitoring the loss of mass, and he has to calculate how much HCl there is in the flask at each of these points. So at this point here, no hydrochloric acid has been used in this reaction, but at this point here we've lost some mass, so we have used some hydrochloric acid, but there's quite a bit left. But what's the concentration of that that's left? Obviously it's going to be reducing, so we need to be able to calculate that. Now I always like to write the equation first, so I actually know what I'm dealing with. So I've got zinc, it's solid zinc. I'm not going to put the states in it. Oh, I think I will, why not? And it's reacting with hydrochloric acid, and that's aqueous, and that's going to give us zinc chloride and hydrogen's a gas. So we know that that's going to go off. The zinc chloride is aqueous. Okay, so that's in solution. Is that balanced? Well, no it isn't, because we've got 2 chlorines here and 2 hydrogens here, and we've only got 1 chlorine and 1 hydrogen. So pop a 2 in front of that, and it is balanced now. So I'm having to calculate the concentration of hydrochloric acid, and I'm losing hydrogen. So this is tracking really how much hydrogen I've lost. So from the stoichiometry of this, from the ratios of this, I've got 2 moles of hydrochloric acid. They're going to react to give me 1 mole of hydrogen gas. So that's going to come in handy a little bit later on. So that's the first thing that I do, and I'm going to leave that as it is. Okay, so now what I'm going to do is I'm going to work out how much mass has been lost at each time point. Okay, so 0, well I haven't lost any mass. My initial mass was 389, and then I'm going to take away whatever is left behind, and that would give me the mass lost. So mass lost, I didn't in grams, I didn't lose any. And here we've got 10 seconds, and that would be 389 take away 388.97. At 20 seconds it's 389 take away 388.95. At 30 seconds 389 take away 388.93. At 40 seconds 389 take away, it should be 0.00, it's giving it as 0.00, sorry, that was my fault. Okay, so 389.93, 388.91, oops, 1. 50 seconds is 389.00 take away 388.89, and at 60 seconds 389.00 take away 388.87. Okay, so I'm going to do those calculations and I will come back. Okay, so I've done the calculations, and we can see that the mass lost at the start of the reaction, there was no mass lost, but then as the reaction progressed, we were losing more and more mass, and so initially 0.03, and after 60 seconds we'd lost 0.13 grams. Okay, so we've worked out that. Now, using mole calculations, we can convert that mass lost into moles. Okay, so molecular mass, mass in grams, and number of moles. So I want the number of moles. So let me see. N equals mass divided by molecular mass. The molecular mass of hydrogen is 2. So the number of moles is 0. So I'm going to put that here, moles. 0.03 divided by 2, which is 0.015. 0.05 divided by 2, 0.07 divided by 2 equals 0.09 divided by 2 equals 0.11 divided by 2, 0.13 divided by 2. Okay, so I'm going to take each of those masses and divide it by the molecular mass of hydrogen, which I've got here. So I'm just going to work that out. Okay, so the number of moles of hydrogen that I have generated is 0.015, 0.025, 0.035, 0.045, 0.055 and 0.065. Okay, so that's fantastic, because that's going to tell me how much hydrochloric acid I have at each of these temperatures at times. So the moles of HCl at each time is, so we can see from the stoichiometry, for every 1 mole of hydrogen I've produced, I would have used 2 moles of hydrochloric acid. So at 0 I have used no moles of hydrochloric acid. We've got 10 seconds, 20, 30, 40, 50, 60, so that's the time interval. And at 10 seconds it's 0.015 times 2, which is 0.03 moles. This is 0.025 times 2, which is 0.05 moles. At 30, 0.035 times 2 equals 0.07 moles. 0.045 times 2 equals 0.09 moles. 0.055 times 2 equals 0.11 moles, and 0.065 times 2 equals 0.13 moles. Now, as I did that, what my head was thinking was, geez, that's the same as this, but I've got to remember this is grams. So this column here is grams of hydrogen, not moles of hydrogen. Here's the moles of hydrogen, and that equates to this moles of hydrochloric acid. So I can see how much hydrochloric acid I have used. So it's moles of hydrochloric acid used. So how much do I have left? Okay, so the amount I have left is the amount that I started with, take away the amount I've used. Okay, so I'm going to do that. Okay, so we can see here the amount of hydrochloric acid I had to begin with is 225 centimeters cubed over 1 molar solution. So the moles of HCl at the start is the concentration times the volume. Okay, the concentration times the volume. So the concentration is 1.0 mole. The volume is 255 centimeters cubed, but I've got to change it to decimeters cubed. And so when I do that, 255 divided by 1000 equals 0.255 moles. So that's how much HCl I had at the beginning. So how much HCl did I have left when the reaction was going? So I'm going to put the time here again. Time 0, 10, 20, 30, 40, 50, 60, and it will be how much I had at the beginning take away how much I used. And at the beginning I didn't use any, so that's how much I've got left. So that's what I've got left. Okay, so I'll do the same for all of these. Let me look at the moles, use this moles figure here. There we go. Just move that over. This is what I've calculated, so I'm going to be using this. So 0.255 is what I had at the start. Take away 0.03 moles. I'll work that out in a minute. 0.255 moles at 20, that's what I had at the start. Take away 0.05 moles. 0.255, take away what did I use at, what was this, 30, 0.07, 0.255, take away 0.09. At 50 seconds, how much did I use? I used 0.11, take away 0.11. And at 60 seconds I used 0.13, take away 0.13. Okay, so I'll do that calculation and work out how many moles of HCl I have left after this reaction has finished. Okay, so I've done those calculations, and we can see that the amount of HCl, the number of moles of HCl that I've got left after this reaction has decreased. So initially there was no reaction, so I had 0.255 moles of HCl in the conical flask, but as the reaction proceeded I was using that HCl, and so after 10 seconds I'd only got 0.225 moles. After 20 seconds 0.205 moles, until we got to 60 seconds when all I had left was 0.125 moles of HCl. That's moles of HCl left. Okay, so now from here I can work out the concentration. Through the course of the reaction I'm not going to be changing the volume of water or the volume of the solution. It's going to stay more or less as it is, which is 225 centimeters cubed. So what I can do here, 225. Okay, I've just looked at that and I can see that I've made an error. That should be, it's not 255 but 225. Okay, so I'm just going to go and change these because I've read the question incorrectly, and that is 225, not 255. Okay, so that's looking better. So you can see even I can misread the numbers and translate. If that happened in an exam, then you would lose the mark for putting the wrong number, but as long as everything else proceeded through, you would gain the mark for that. Right, so let's have a look. So we've got our initial amount of hydrochloric acid is 0.225 moles, and we can see it decreases as the reaction goes on until we're left with 0.095 moles of HCl. So from here, as I was saying, the volume is 0.225 decimeters cubed. We can work out the concentration at each time point. So the concentration is moles divided by volume. Okay, so 0, 10, 20, 30, 40, 40, 50, 60. So that's the time, the seconds, and we can work out the concentration. So we know the number of moles, 0.225 divided by the volume, 0.225. So the first one, the moles, is mole per decimeter cubed, 1 mole per decimeter cubed, which is good because that's what we started with. And then we can work it out for 10 seconds. So 0.195 divided by 0.225. I will work that out in a minute. 0.175 divided by 0.225 equals 0.155 divided by 0.225. 0.135 divided by 0.225. 0.0875 divided by 0.225. And 0.095 that's bigger than that. That's not right. Let me just check that. 0.225 take away 0.13 equals 0.095. That's correct. Let me check that one. 0.225 take away 0.11. That should be 0.115. So that's 0.115. So this is 0.115. And that's 0.05. Okay, so it's always worth, as you're working down, to make sure that the numbers sort of run as you would expect, and if they don't, there's something wrong, and it's always worth going back for a second check. Okay, so I'm going to calculate the concentration now. Okay, so having calculated the concentration, we can see that the concentration decreases as the reaction proceeds, which is what you would expect. So we go from a concentration of 1 down to a concentration of 0.422, and they're all moles per decimeter cubed. So always make sure your units are in there. Right, so that's how you would calculate the concentration as a reaction is proceeding, and the next part of this is to then plot the graphs. From that we'll be looking at tangents to the curve. Okay, so we're going to plot a graph of concentration versus time. Okay, so I'm just going to quickly go through what we did. So we were given a mass, and we were seeing that the mass was being lost, so we were losing a gas. We worked out the equation, so we could see the stoichiometry and the ratio of the hydrogen against the reactant it wanted us to calculate the concentration of, which in this question was hydrochloric acid. It wanted the concentration of hydrochloric acid. So we then looked at the loss, the mass lost as the reaction went ahead, and we got the figure in grams. That's the mass of hydrogen that was lost, because that's the only gas that's in here. And then we converted that grams to moles, and hydrogen is bimolecular, so H2, so the mass of hydrogen molecule is 2, and when we did that we were able to work out the number of moles of hydrogen lost. From the stoichiometry we know that for every 1 mole of hydrogen lost, that means we've used 2 moles of hydrochloric acid. So we can work out how much hydrochloric acid we've used. So as the time was going along, here's the amount of hydrochloric acid that we have used in moles. So we can calculate the number of moles of hydrochloric acid used. We can then work out how much hydrochloric acid is left behind in the reaction flask, and we can do that because we know how much hydrochloric acid we had to begin with, because we were given that information at the start. It was 225 centimeters cubed, and it was a 1 mole per decimeter cubed solution, so we were already given that. So moles of hydrochloric acid at the start was the concentration times the volume. So the concentration was 1 and the volume was 225 over 1000. Remember to make it into decimeters cubed. And we can work out So that gave us 0.225 moles of hydrochloric acid at the very beginning. We know how much we used, so we can now work, so this is how much we used, so we can work out how much is left. So we've got the initial amount of hydrochloric acid, and we take away the amount we've used, and that gives us the amount that's left in that reaction flask. From there we can calculate the concentration. We know concentration is moles divided by volume, and the volume of that reactant isn't going to change appreciably, so it is going to stay at 225 centimeters cubed, or 0.225 decimeters cubed. So we can work out the concentration of the hydrochloric acid that's left. So the concentration is the number of moles divided by the volume. We've worked out the number of moles. So here are all the number of moles, and the volume is 0.225 decimeters cubed. So when we do that, moles divided by volume, this is the concentration of the hydrochloric acid that is left behind. And from this we can plot the concentration against the time.